So, proving the energy reactance with adiabatically driven quantum dots. I imagine that maybe you have in mind some of these questions. What I'm talking about, what is the energy reactance, why it is important, when it's manifested, and how to prove it. Because the concept of the energy reactance was recently introduced, just a few years before, up to now, and it is still a topic of discussion. So during the first part of the talk, I will make an introduction based on these three questions, and then I will pass to the goal of this talk, that is to show how to prove the existence or the relevance of the energy reactance into the definition of the heat flux. And the talk will be based in a work I did together with Liliana, David, and Misha Moskalet, that was published recently at the beginning of the year. So let's start. Recently, there has been an exciting experimental activity on search on control on-demand coherent transport in the time domain. This exciting activity has started with the experimental implementation and generation of quantum capacitors, single particles emitter, generation of levitons, for example. These developments are based on the application of some AC driving into a nanoscale system. And so these developments have opened a way toward the study and then control of time-dependent charge and energy flows in the time domain. This is something that is very important in this talk, that we will focus on the study of charge and energy flows in the time domain, when we want to study the charge and the heat as a function of time. So the typical system are composed by some nanoscale system component confining a small number of particles in contact with macroscopic reservoirs, and they are driven out of equilibrium by the application of some AC driving. So all the study of the energy transport will be behind the usual thermodynamics. And the main problem is that we have to identify which portion of the total energy corresponds to heat. So this is the main question right now. Because of course in DC transport and for system at equilibrium, any of you can provide a definition of the heat. But for a system that is within the nanoscale and out of equilibrium, this is a more complex and deep issue. The main problem, it's not a problem, the main point, is that the role of the tunneling region that is playing, is storing some energy. I will explain it in detail in the next slide. So let me explain it. Imagine that you have a nanoscale system denoted with this circle here and this S in black, and that is coupled to some macroscopic reservoir at a fixed chemical potential and a fixed temperature. And let's focus first on the exchange of particles. At the level of the conservation law, we know that all the electrons or particles that are leaving the nanoscale system will enter the macroscopic reservoir, so that we have this conservation law. This is the number of particles entering the macroscopic reservoir. That should be minus the number of particles entering the nano device. But in this case, there is no any contribution of the tunneling region, because the tunneling region here is just a way for letting particles pass from one side of the sample to another, and that's all. But in the case of the energy, it's a bit different, because when you apply a time-dependent gate into your system, we are not only injecting and inducing some exchange current of heat and charge, but you are also injecting some energy into your system, and this energy will be stored in the three components of the setup. Will be stored in the nanosystem, in the tunneling region, but also in the reservoir. So that the conservation law does not only involve the energy stored in the reservoir and at the nanoscale system, but also involves an energy that comes from is a contribution of the tunneling region. And this term is disregarded in classical thermodynamics because it's too small. But when you are studying a nanoscale system out of equilibrium, the energy stored in the nanoscale system is comparable to the energy stored at the tunneling region, so that it cannot be neglected anymore. And we, Liliana, David, Misha, and also Shamsulim, name this contribution energy reactance in analogy to the electrical reactance, inspired on the electrical reactance. And we can see that this is only manifested in time-dependent transport only. If you see all the quantities averaged over one period, it will be 0. So you have to study the current as a function of time to see the contribution of this term, so that we say that this term is of AC nature. So we started studying this problem with a very simple model, but simple but not meaningless. It was just a single level connected to a macroscopic reservoir. At this level was driven by the application of a periodic gate. And we propose this expression for the heat entering a store at the reservoir that has a contribution of course, the free energy, the chemical energy, but it has also this half of the energy reactance here. And we show in this was the previous work I show you, in these 3 works, that this definition is in full agreement with the thermodynamic laws. For example, it satisfies this point here. For example, at low temperatures, it follows this Joule law. For example, this is the heat, and this is the number of particles square. And when the temperature of the reservoir is close to 0, the relation between the heat and the charge square is a line. And the slope of this linear relation is a resistance. It's a constant and universal resistance, that is the Buteyko resistance. And on the other hand, if you consider another definition of the heat, this one that does not take into account this contribution, of course you can consider another fraction of this energy reactance, which just show an extreme, just avoid this contribution. We show that it does not follow Joule law. For example, also it attains some negative values at t equal to 0, and this cannot be possible because this means that you are extracting some heat from a reservoir that is at 0 temperature, and this cannot be possible. And well, this definition is also good because it leads to positive entropy production, gives the same result, reconciles the green function formalism and the scattering matrix formalism. You can use whatever you want and you will arrive at the same result. This contribution, a more or less naive way of thinking it, is just because in the scattering matrix you don't have the Tanner region, so you can think that half of the, more or less, half of the Tanner region belongs to the nanoscale system, and the other half belongs to the macroscopic reservoir. And also, this was shown by Guillaume Roselot, Rosa, and Jean-Sue Lim, predict some correct frequency parity properties of the response functions. So, of course, I want you to understand that this problem of the definition of the heat is very important. It's a fundamental problem, because if you want to study and control the time-resolved current, you have to really know how to define it. So, well, let's pass now to the goal of this talk, that is the proof of this energy reactance. So, we propose, sorry for the experimentalist, an experimental setup. The system we have in mind is a resonant level, is this blue disk here, which is driven out of the equilibrium by the application of this periodic driving. And it is in contact with some grounded reservoir, which has a fixed temperature and a fixed chemical potential. This coupling can be arbitrary. And we focus on the adiabatic regime, so this potential evolves in time very slowly. And we attach to this single level a flotating contact, and this is very important to understand what the flotating contact is. It's a small conductor that was assumed to have a relaxation rate for charge and heat and energy much faster than many other characteristic time of the system. So it is supposed to be at thermal equilibrium at every instant of time, so it can adjust its chemical potential mu and its temperature in order to prevent charge and heat accumulation of it. So at every instant of time, we have this temperature at this chemical potential satisfying the simultaneous condition of vanishing heat. This is the heat flowing in this contact and vanishing current. And this assumption is reasonable if the driving is very slow. So the flotating contact has enough time to adjust to this variation. And we propose, I will show you, that both the temperature and the chemical potential are very sensitive. The prediction of the measurement will be very sensitive to the definition of the heat we have. So that we can measure the temperature by the use of a thermometer and the voltage by using a voltage probe and see what happens. So now the main point I would like to be clear is that the fact of the strongly sensitivity of both these quantities as a function, depending on the definition of the heat, makes that by sensing and measuring these two quantities constitute a good experimental test for the energy reactance, the existence of the energy reactance, and the importance of the energy reactance into the definition of the heat. So I will show you that if we take the energy reactance into account, the half of the energy reactance into account into the definition of the heat, we predict a universal response of a thermometer in the sense that the temperature of the of the rotating contact will be constant and equal to the temperature of the reservoir. Something that is very important is that we use this index here, I forgot to mention before, and not this kind of dependence on time, to stress that the temperature and the chemical potential depends on time, but not because the reservoir is out of equilibrium, but on the other hand, on the contrary, they depend on time in a frozen way, in the sense that the rotating contact is at equilibrium at every instant of time, like in a snapshot. So we predict this result of a measurement of the temperature and the chemical potential. We see that the temperature remains constant and the chemical potential evolves in time, but following the variation in time of the driving. And this is a universal response in the sense that it does not depend on the spectral properties of the system. And on the contrary, if we don't take into account this contribution, again, you can consider another fraction of the energy reactance. T and mu follow a non-universal time-dependent pattern. And so in the following slide, I will show you how to prove it. So imagine that, let me start from the deviation of the temperature of the rotating contact and of the chemical potential from its reference value that are fixed, that are the temperature of the reservoir and the its chemical potential. So in the adiabatic regime, this frequency is too small. And since the temperature and the chemical potential are both following this variation in time of the driving, the deviation will be also small, will be comparable to this small frequency. So we can treat our problem with the linear response regime. So imagine that we collect the charge current entering the rotating contact and the heat current, and we collect these fluxes into this vector shape. On the other hand, we have the affinities, that the affinities are just the forces that generate transport. Transport here in this setup is generated by the application, by the existence of this different of temperature, different of chemical potential, but also because of the driving. So we can expand the fluxes up to linear response in the affinities in terms of this coefficient, which are the linear response coefficient, collected in this matrix lambda. And of course, each component of this matrix lambda has a physical meaning. For example, remember that shade 1 corresponds to the current and shade 2 corresponds to the heat. So this line will be related to the charge flux, and the line of the bottom will be related to the heat. So this describes the charge that is generated because of this delta mu, so it will be the electrical conductance. In the same way, this will be the thermal conductance. And gamma 1, 2 and lambda 2, 1 will be related via this Onsager-like relation, and they will describe the thermoelectric effect. This will be the Seebeck coefficient, and this will be the Peltier coefficient. And this block here is very different. The nature of this block here is very different from the nature of this column here, because this is because of DC transport. This is describe the charge that are generated via due to this delta T and this delta mu. But this column here describe pumping, because it's talking about the fluxes that are generated because of this frequency. So you can compute the coefficient with the formalism you prefer. We use the Autos equilibrium Keldysh formalism, but we can use whatever you prefer. And we find that the equal to 3 describes pumping, and it will be related with the frozen density of the state, that is the density of the state evaluated at the Hamiltonian, at the frozen time t at equilibrium. And as you can see here, it will be proportional to the variation in time of this driving. So it is pumping. So we can, by imposing the condition of vanishing of 0 fluxes, 0 charge, and 0 heat, we can find an expression for the deviation of the temperature of the flotating contact and for the deviation of the chemical potential. And you will find a simple 2x2 linear set of equations with the solution. It's not very important the shape of the solution, but yes, the result, yes. So these coefficients satisfy in the case of a single level, this is important, these relations. And this relation leads to the universal response I showed you before. The prediction of the constant temperature, because remember that this is the deviation, so this means that the temperature of the rotating contact will be equal to the temperature of the main reservoir, and that the deviation of the chemical potential will follow the changes in time of the potential we are applying. And the prediction, I would like to stress here that the prediction of this universal response constitutes a proof of the energy reactance into the definition, the presence of the energy reactance into the definition of the heat. And this result is independent of the temperature. If you go to even for 0 temperature, in the limit of low temperature, where linear response is not valid anymore, you have to consider any other extra terms because some linear response coefficients are 0. And it's also independent of the coupling between the level and the flotating contact. In order to show that this prediction is very sensitive to the definition of the heat, we take into account another definition that has only the internal energy and the chemical energy, but not any contribution of the tunneling region. So in this case, because since we are just changing the heat that is correspond to shade 2, we have to change only the coefficient of the bottom line of this matrix. So we have to change lambda to shape, but another lambda hat to shape. And since this tunneling contribution is only of AC nature, it will be proportional to the, also proportional to the variation in time of the AC driving, so that the only coefficient at the end that will change is the coefficient related with pumping, but the DC block will remain the same. In this case, we arrive to different patterns. In this case, I'm showing the temperature of the deviation of the temperature of the rotating contact as a function of time within a period of the driving potential. And as you can see, it will be not universal anymore. This behavior will depend on the spectral properties of the system, of the device, but also on the temperature. And as you can see, as the temperature increases, we are, for example, for the green curve, the amplitude decreases, and this means that in the classical high temperature limit, both predictions will be the same, because in the classical high temperature limit, the tunneling contribution, the tunneling does not contribute to the energy, to the heat. So for temperatures around, for example, 100 millikelvins, the maximum amplitude we are attaining is around 10 millikelvin, that is measurable. And the most delicate thing here is that, for example, if the hybridization with the reservoirs is more or less 1 micro electron volts, this kind of frequencies of the order of 0.1 gigahertz are safely within the adiabatic regime. And the changes here, the fluctuation here as a function of time, will take place within the nanosecond scale. But this can be reached. I mean, there are these two recent publications from the group of Pecola that they can perform fast thermometry with some Josephson junctions and by the use of superconductors. So the summary of my talk and what I want you to remember, the message of this talk is that we show that the behavior of the time resolved chemical potential and the temperature of the flotating contact is strongly sensitive to the definition of the heat, so that the definition of the heat flux can be verified by measuring the temperature of the flotating contact and also the chemical potential. And we predict this result, a constant temperature and chemical potential that follows the variation of time of the driving, that is universal, in the case in which the half of the tunneling contribution is taken into account into the definition of the heat. And on the other hand, if you take into account another definition of the heat, what you will measure will be really different and will have a non-universal time-dependent pattern. Well, before finish, I would like to thank the co-authors of this work, Liliana, Michael, and David, and also my affiliation at the moment of this work, that was the Universidad of San Martin, the International Center of Advanced Studies, and also the hospitality of the ICTP that let me work there for a while. And also thank you to all of you for your attention.